Hello and welcome back. What I want to talk about is what is the ASD and LRFD. The allowable stress design and load and resistance factor design both are two different methods that we use to design structural member. In steel design, in timber design, but in concrete and bridge design, they only use load and resistance factor design. So what are they? Both uses the same structural analysis, and both method uses a limit state. Limit state which is based on strength and serviceability. In strength will be you have a limit on your yielding, so you don't want to do over yielding, how much stress you want to exert. And then the serviceability would be deflection limit, for example. When we design a structural member, we design them based on applied load. And loads are different. I highly recommend you watch my loads on dead load, life load, and so on and so forth on my video. The links are down below. So when we design them based on these applied loads, and when we calculate the loads, both method uses different calculation, which we'll get into when we do an example later on. But we always, these both method uses as some type of a numerical margin between the resistance of the material, the member, the capacity of the material, and the applied load. And both uses the same margin, but they have a different ways. If we look at the history of load and resistance factor design, it started in 1986, around 1986. Prior to 1986, everything was designed completely on allowable stress design method. And from 1986, it started taking off. It was a new method that was developed. Most universities caught on to it, and they adopted 100%. And they had a strong push in the universities. But the industry still was reluctant. Why? Because in 1970s, 80s, and 90s, the engineers that were working out there, they were very comfortable with allowable stress design, and they used that. And if both methods are accepted in steel design and in timber design, what bother making a change? They had confidence in it, and it worked. So industry is still lagging behind from moving over to load and resistance factor design. In fact, somebody correct me if I'm wrong, go ahead, do your research. In the state of California, when you design a hospital and a school, you are required to use allowable stress design method because it has a bigger safety factor than load and resistance factor design. And we know the load and resistance factor design is very efficient and very consistent, and all you have to do size up your member if you're not comfortable with it. Both method, it uses the nominal strength, and the nominal strength is basically the resistance of the material against the applied load, so it will not fail. And that resistant material is without the safety factor of safety. In LRFD, we use phi, which is a resistance factor, which is less than 1 normally, 0.9 or less. And then in allowable stress design, we use omega as a safety factor of safety, which is more than 1 usually. In load and resistance factor design, when we calculate our load, depend what type of load we have. So if you have dead load, life load, rain load, snail load, using a load combination, as you can see on the screen, which is from IBC, International Building Code, or from ASCE, these load combination is used, and the largest number of those will be used to calculate the load combination. And you have a factor in front of the load, and this load factor, which is normally bigger than 1, and that's basically they represent the uncertainty of the However, in allowable stress design, we just basically add both load. In both system, both method, the goal is that the applied load should be less than the capacity of the material, and that's why we have this formula here, and we're going to do example to explain these, what I mean by that. So now we have this problem, which is a tension member, and it says the length has to be 30 feet and use W12, and they're giving you a dead load of 130 kips and a live load of 110 kips. Steel is a 50 KSI. The bolt diameter is 7/8. They have 4-inch spacing between them. One of the first things we're going to go do, we're going to go ahead and calculate the applied load. And in here, we're going to use either IBC 2018 or a CO7 for the load combination for LRFD. And you can see basically number 1 or number 2 apply. We're going to go to number 2 because you know number 1, which is, let me just do it, 1.4 times D, and that become 1.4 times 130, and that comes out to 182 kips. But if I go to the combination number 2, we usually pick the largest of the two, which is, we say basically PU, both of them are PU, 1.2D plus 1.6L. And that's going to win anyway, so I'm going to write down here, PU is equal 1.2 times 130 plus 1.6 times 110, and that gave me 332 kips. Now let's do the same thing for ASD. It's basically both load combined. We call that PA, and that is 110 plus 130. So 240 kips. There it is. Now from here, if you're experienced designer, you already know you have W12. So you're going to go ahead and pick a size and then you run it through. But in here, since we're beginners, some of you probably never done it, so we're going to go ahead and make an educated guess. And we're going to make an educated guess, and based on that, we can select a size, and then we're going to go ahead and continue with that. So we're going to use the LRFD method for educated guess. Look at what I have on the screen also. We're going to calculate the minimum gross cross-sectional area. Based on that formula, we know it's going to be basically PU divided by phi factor of tension. This is a tension member. Multiplied by FOY. And that came out to 332 kips. 332 kip divided by 0.9 times 50. So that gives me about 7.38 inch square. But we know we have a bolt, so we got holes in there. The other formula that's right there, we got to use that one. And basically that is AG is equal PU divided by phi T FU times U, and plus the estimated hole. There's a problem here. We don't know U, and this is where we have to guess at it. And if you look at the table, that's a table D3 from D3.1 table. It's on the board. That's in the page, that big ASC manual is in the page 16.1-30. We look at the case number 7, And looking at the case number, so on the bottom part, so we're going to assume, let's assume that because of the flange thickness, we're going to say U is equal 0.85. And again, we made an assumption here to make an educated guess. So if we use 0.85 right there, then we're going to go ahead and go back and plug into this formula. We're going to say, okay, AG is equal, there's room there, that's right. AG, divide that by phi t, which is in this case, our phi t is 0.75. Multiplied by FAU is 65 KSI. And multiplied by U, which is 0.85. And then plus, we have 1, 2, 3, 4 bolts. And is 7, 8 diameter. The ASE says for bolt hole in steel, you add 1/16. In timber, it used to be 1/8. So we're going to go 1/16. And then we have time flange thickness. When we assume here, we said let's assume for this, let's say BF assumption was 0.38. Again, this is based on assumption. How do I get this assumption is important because you go to table, let me bring it up, look at the W12, and then we pick out the thickness of the one of the W12, and that's where we're going to use here. So that's going to be 1/16 plus, that's a 0.38. And if I calculate all that, come out to, AG comes out to 9.53 inch square, and this is control compared to one we have up there without the hole, obviously. So now we can go in, look under the table, but that same table right there is fine, and look at find the area in W12 that is a little bit bigger than this. This information, we want to know that, I need some room here. Let me erase up here. Stay down here. So we're going to say with our minimum, our radius of gyration, it's going to be R is equal L divided by 300. And that's going to become, we had 12 inch times 30 feet divided by 300. And that comes out to a 1.2. So we're going to go back and select a size using that same table. Look at the same table, and based on the table, based on these criteria that we have, we're going to pick one area bigger than a 9.5. So we're going to say let's try W 12 by 35, which we have those information. We can pick out those information from the table. We're going to have AG comes out to 10.3 inch square, and we have D is equal 12.5, and BF is equal 656. And our radius, our RY is 1.54. RY is 1.54. We good there. And we have the TF. It's 0.520 inch. PN comes out to FOI times AG, which is 50 KSI time the area came out 10.3, and that will give us 515 kips. 515 kips. So keep that number in mind, we need that. So our Pn comes out that. Phi n, phi t actually, and we had Pn, and that is equal, we said this phi t is 0.9 multiplied by 515, and that comes out to 463.5. 463.5, and that is more than the resistance, the applied load. Applied load we had 332 right there. Okay, so now we're going to do the same thing for ASD, and for ASD it's going to be Pn divided by omega, and omega is this was 515 divided by 1.67, and as I have it on the board, what omega and what phi 10 is. Also look at the relationship between these two. So that comes out to 308.4. Comes out more than 240. We're good there too. So now we're going to check for tensile rupture strength. We selected W12 by 35. So the WT, which is half of that we want to use, it's going to become, let me switch here. The WT, it's going to become, we're going to use it for the X bar we're going to actually look for, which is and half of this will be W. 6 by 35 divided by 2 would be 17.5. And we can look that up. It's in a steel book, and you can see that on the screen for WT6 actually. That should be WT. So WT6, let me write that here. Oh, this is make a mess, this color. WT6 by 17.5. And we look up at the chart, the X bar for that comes out to be 1.3 inches. And the length is 8 inches basically. Our length is here 2 times 4 is 8 inches. And then we're going to calculate the U based on a formula from table 3D. So the U, it's going to be, and this is in a case 2. In case 2, we can go ahead and say 1 minus X divided by X bar divided by L. So that comes out to 1 minus 1.3 divided by 8 inches. So that comes out to 0.84. Like I said at the beginning, we look at the case number 2, and we're going to look at the case number 7. And we look at the case number 7. We want to find out where U is going to fall in based on our BF. Is it less than 2/3 of D or more than 2/3 D? And so let's say BF came out to, we know, which we wrote it down in a pre-arrested. It came out to 656. So that should be less than 2/3 of D, which is 2/3 times 12.5, based on the information we have from the table. And that comes out to 8.33 inches. So that checks out. Therefore, U, we can use U equal 0.85. And we have the bigger of these two controls, so 0.85 control. Now we have that, we can go ahead and calculate the AG. Let me write this down. Therefore, our AG comes out to 10.3 inches. We had the area, and minus 4 times 7/8 plus 1/16. That's diameter of the bolt, and we had 4 bolts, 1, 2, 3, 4, and multiply by the thickness, which was 0.520. And if you can see the formula, it's on the board where this come from. And that gives us 8.22 inch square. So now we have that. Then we have got to find the AE. 3D, we know, I have it on the screen from AISCS. We have AAE comes out to 0.85 multiplied by 8.22, and that will give me 699 inch square. So now I can find my PN. So my PN comes out to be FAU time AE. Again, this is based on chapter D, which I have on a board. That's where all these formula come from. So now we have 65 KSI multiplied by 699, and that will give us 454.3 kips. So now we have our PN. We're going to go back up here, and from there we can go ahead calculate our phi time PN. Again, now with this one, because we're doing the rupture case, our phi T comes out to be 0.75. Be careful of that. So I'm going to go ahead and say that was for tension, this was for rupture, so I'm going to say phi T time PN, which is 0.75. Again, look at the board, what I have, and multiply by 454.3, and that comes out to 340.7, which is bigger than 332. You can see this is closer than this. Now we're going to go ahead and do the ASCE, allowable stress design, and that's going to be same thing, PN divided by omega, and our PN came out to be 454.3. However, our omega is equal to, and that will give us 227.1, which it is not bigger than 240. That is no good. Checks out. And here's the difference. Exactly this problem said that. We did this, we used LRFD based on LRFD, load and resistance factor design. We selected the W12 by 35 and checked out fine. Now, using the same size, you go ahead and check it out, and allowable stress design is not going to be fine. So you got to pick up the size, make it a bigger member. And if you go into the, check out the slender ratio, which is basically Ly divided by Ry, and Ly came out to be was 30 by 12, make that to an inch, and I believe Ry, which I erased it, was 1.54, and that comes out to be 234, which is less than a 300-hour limit. So that checks out. But we know this was no good using allowable stress design, so we have to really pick it up. Maybe we can go ahead and try for this size W12 by 40. And if you run that through again, you find out that W12 by 40 will be accepted for allowable stress design. And this was the difference. So what we did here, we used the method of load resistance factor design to select the size of the beam. And then once we selected it, we ran all the number. It was fine here, but it wasn't fine here.